Well, good morning. Thank you so much for joining me. Wasn't kind of expecting that introduction. So my name is Michael Howard. I'm here to talk about one of my favorite topics. I work in the Microsoft Red Team. Probably some of the most talented people I've ever met at Microsoft. Some people call them evil, but not evil. Definitely some of the most talented people I've ever met across the company. I will admit one thing right now, though. The title is actually a bit of a lie. Actually, it's a complete lie. It's not 25 years. And this isn't working. There we go. Let's try to get this to work. I am not moving. Oh, there we go. There we go. There we go. So I say it's 25 years of Microsoft SDL. It actually really isn't. It's not 25 years at all, but it's definitely 25-ish years of the Microsoft SDL. And you'll see why I mention that as I go through the slide deck. A couple of people have asked me about the image that I have on the little blurb about me doing the keynote. And it's actually a photograph of me diving on a very famous shipwreck in New Zealand called the Rainbow Warrior. It's not a great shipwreck. It's not very deep. It's about 80 feet deep. But it's interesting in as much as it's the only shipwreck I've ever actually dived on that's actually been sank twice. It's not often you get to dive on a shipwreck that's sank twice. So anyway, as to the agenda, I say agenda of sorts, and there's a reason why I say that. I've never in my life actually ever managed to stick to an agenda, ever. It's just something I've never been able to do. Hopefully one day I will stick to the agenda, but I'll be honest with you, today is not that day. I'm not going to stick to the agenda today at all. All right, so what is the Microsoft Security Development Lifecycle? It's something that was introduced almost 25 years ago, really in a response to vulnerabilities that we had across the company, most notably in Windows. It's a series of recommendations and requirements. It's things that you should do and things that you must do to help secure products. It's updated constantly, and that's really important. But also, we've removed things from the SDL. And this is a very important point. I really want to stress this. You can't just keep adding more and more cognitive burden to your development environments and expecting engineers to stay on top of it. If something doesn't work, remove it. If you need to replace it with something else, then replace it. But it's really important that when you're evolving these environments, that you don't just keep growing it and making it harder and harder and harder. And it eventually just becomes a tax that engineering staff have to pay. So I really want to stress that. And a really good example of that is some of our static analysis tools. There were some tools that just became outdated and replaced with better ones. So rather than requiring the old ones, we just got rid of them. So some literary history. So I've written a few books across the years. Probably the most well-known one is Writing Secure Code that I did with David LeBlanc. David was in Office at the time, and I was in Windows at the time. Two teams that absolutely adored each other. That is a joke, by the way. But we wrote Writing Secure Code together, and that really sort of put David and I essentially on the map. It became sort of our magnum opus. I also wrote the book, Security Development Lifecycle, with my manager at the time, Steve Lipner. Now, what's really interesting about these books, though, is that two of them, Building Secure Software and Writing Secure Code, came out about 3 months apart. Building Secure Software was written by good friends of ours, Gary McGraw and John Viega. David and I went on to write other books with John Viega. What was interesting is that book came out 3 months before Writing Secure Code. Ours is very Windows-centric, theirs is very Linux and open source-centric. We both published roughly kind of very similar books, roughly very similar timeframes. We didn't know each other were writing the same books. We didn't know that. But what's interesting is how did that happen? Like, why did two totally disparate books get released at kind of the same time? And we believe that the industry recognized that there was a sea change happening in a focus on building more secure products and a recognition of vulnerabilities that came out. I will also, this is the first time I've actually even brought this up because we literally got the cover just a couple of days ago. I actually got another book coming out, Threat-Driven Software Development. It'll be out in June. I wrote that with three very good friends of mine. So Lee Holmes, he was the security program manager on PowerShell back in the day when it started out as Monad. And Sean Hernam works in Azure Security. And what makes this book different, I think, is that, so Sherrod DeGrippo, she's a deputy CISO And she's probably one of the world's most preeminent experts on threat intelligence. And she helped us write this book. Every chapter actually has some flavor text at the beginning that frames that chapter through the lens of threat intel. And the whole point of this is that you can't just keep saying, hey, do these things, do this thing, do this security thing, do this security thing. You got to look at it through the lens of threat actors. Is that actually what they're doing? Because if not, you may be wasting your time in terms of prioritization of time and effort. So that's why we wrote this book. All right, so let's get back to SDL. Actually, before I get onto this slide, which shows the evolution of SDL, I want to give you a little bit of prehistory. Before the SDL, there's a thing called SWI, the Secure Windows Initiative. There was less than 10 of us working on it. When I say less than 10, more like 5, but there's a lot less than 10 people working on this. We were all technically in Windows, and our job was really to focus. We were the first bunch of people to really focus on securing features versus security features. And it's a very, very big, very different mindset. So we had these things called security bug bashes. We had bug bashes with Windows, with Office, with Exchange, with SQL Server, with the developer division, with all sorts of divisions across Microsoft. And it was really just a day's effort to look for security vulnerabilities. I primarily looked after all the developers, all the people actually writing the code. A colleague of mine, Jason Garms, mainly focused on working with program managers, working on threat models and secure design. And another friend of ours, Chris Walker, he worked mainly with the testers, working on building test plans and, most importantly, building fuzz tests as well. The whole point of these bug bashes, there would be some education at the beginning of the day, and then we would have the rest of the day we'd be looking for bugs, security vulnerabilities. And then we would triage them later, basically just file bugs. All we cared about was just file bugs, and then we would triage them. The problem with that process is we were basically having people write code that wasn't fantastic, and then have a security bug bash looking for security bugs and fix all those security vulnerabilities. You can't do that. It's absolutely unsustainable. They were fun, I'll give you that. They were certainly fun. And you could even argue that the real goal wasn't even to look for security vulnerabilities. It was really there for education. You could think of it as education at the beginning, and then some homework for the rest of the day, and then hopefully further on, people would start to write more secure software because of the bug bashes. But it's just not scalable. We had prizes as well, but it's just not scalable. I also had a personal baptism of fire. So I was actually, some of you will snigger when I tell you this, I was actually the security program manager for IIS, for Internet Information Server, for a long time. Primarily late version of IIS 3, then 4, then 5, and then early versions of 6. IIS 5 especially had fantastic security features. It was the first web server that had built-in Kerberos authentication. We had really tight certificate services integration. We had digest authentication. We had certificate revocation. We had the whole 9 yards, right? It was really sort of security buzzword compliant. But it also had lots of security vulnerabilities in it. In fact, 3, 4, and 5 all had lots of security vulnerabilities. How many of you ever remember Code Red? The worm? Yep. NIMDA, another one. They were all on my watch. I'll be honest with you, they're all on my watch. Not exactly something I'm particularly proud of, but you learn from these things. Most of the vulnerabilities were memory safety issues and canonicalization problems. And then other ones, we saw a real rise in SQL injection as well, because we had active server pages with COM integration, which then had SQL Server integration, which was just an avenue for SQL injection. So back then, my lexicon of words that were thrown around all the time were things like ACLs, DACLs, SACLs, SIDs, tokens, privileges, logon sessions, split tokens, all this stuff that was all Windows security features. And that was really IIS 3, 4, and 5. But then post IIS 5, IIS 6, by the way, the code name for IIS 6 was Kevlar. My idea for the code name was going to be Voyager, as in the Voyager spacecraft. It just keeps on going. But Kevlar was settled on because it's bulletproof. And IIS 6, I'll go down, I've said this publicly many, many times, IIS 6 is an incredibly secure and incredibly robust web server, and always has been, since 6. 3, 4, 5, not so much. But 6 onwards, it's been a fantastic web server. But what was interesting there is we basically just threw a whole bunch of code away and started from scratch and built it understanding the threats that web servers were exposed to. And my lexicon changed completely to things like dynamic analysis, threat modeling, authorization, authentication, SQL injection, crypto, cross-site scripting, fuzz testing, all these things. My lexicon completely changed. My career went from building security features to securing features, and it is a completely different mindset. So I really want to stress that last point down there. Security features does not equal security features. Secure features does not equal security features. So you go back to the books. If you look at the very first book that I worked on, which is around the Windows 2000 days, that was all about security features. All the books I've worked on since then have been about securing features. Very different mindset. So let's now go back to the SDL evolution itself. So when SDL started back in the day, we had code red. It was a security vulnerability in IIS 4 and 5. Yes, 4 and 5. Then we had the trustworthy computing memo came out. And then we had SQL Slammer, which is a worm that infected SQL Server. How many of you have heard of or know of SQL Slammer? Okay, a few of you. Then we invented the SDL, the Security Development Lifecycle. Again, it was a small group of people who started it out, and we started pushing it across the whole company and made it a requirement across the company. Then we started to evolve it. We shipped it to customers. We made a lot of documentation available to customers as well as tools. We then started to focus on SDL for Agile, because you could argue that SDL back then was very heavyweight, was kind of quite waterfall-y, and it didn't really match the development practices of other development teams across Microsoft who had adopted Agile methods. Moving through the PSN hack network, the reason why that PSN attack, PlayStation Network attack, was so interesting is because we were learning from other people's mistakes. We weren't just looking at our own mistakes, we were looking at everyone else's mistakes as well. And what could we learn from those mistakes and feed those into our development practices too? Finally, around SDL version 7, we now got this regular cadence of about once every 6 months, which then became once a year. Then SolarWinds came out. Very, very well-known, very famous supply chain attack. Then there was Executive Order 14028 came out. And then finally, we had SDL Continuous Assurance, which I'll talk about in a moment. But I wanted to spend just a split second on Executive Order 14028, which came out from the White House. This was really a sort of documentation around this is what the industry should do. If you're providing software or services to the federal government, the US federal government, then you need to do these things. A big part of that is also SP 800-218, which is around secure software development. That document makes a lot of references to the Microsoft SDL, makes a lot of cross-references. In Europe, there's also ISO 27034-1, and a big part of ISO 27034-1 is Annex A, which is a complete run-through of how to map the Microsoft SDL to the requirements in 27034. So the SDL has had a lot of impact across the world, not just in the US. All right, let's look at a little bit of code. So I mentioned Slammer before, which is a security vulnerability in SQL Server. This is the essence of the code. There's actually a lot more to the code than this. If you're really interested, up on my GitHub, I have a repo that actually has a more complete source code sample of the bug that led to the Slammer worm. Essentially, we've got a receive from. Receive from is a UDP read, right? Which immediately the hairs on the back of your head should stand up because that's a UDP read, which means that it's completely unauthenticated, right? So people are just dropping packets on the network that are not authenticated, and that's where the vulnerability exists. It ends up finding its way into SSRP enum. And that's where the problems really begin, because it can take 256 bytes off the network, but it then copies it into a 128-byte buffer, and that's a buffer overrun, right? And it's a stat-based buffer overrun, which is the most lethal of all the buffer overrun types. So what's interesting, if you look at that bug, and you say, okay, how could SDL have prevented that if SDL had existed at the time? And it basically, I'll go out and say right now, that bug could never happen today at Microsoft. And I would hope across the industry because of things that we've done in our tooling. So for example, in Visual Studio today, if you try to compile that, or Visual C++, it won't compile. Because sprintf, which is where the vulnerability lies, is deprecated. completely deprecates it. So you get a C4996 warning, and your compilation would stop. Now, normally a level 4 warning is just a warning. But in the case of Visual C++, we actually stop compilation. It's an error. It's actually a fatal error. Also, if you turn off C4996 warnings, which is a bad idea, but if you did, then ban.h, which is the header file that we require, would also prevent it. Visual Studio will give you red squigglies underneath sprintf to show that there's a problem. If you use semgrep, which is a tool that we use quite a bit at Microsoft, that will also detect the problem in the editor. CoQL and Prefast, which is two static analysis tools, they would find the same bug in CI/CD pipelines. How many of you are familiar with CoQL? Okay. So CoQL is a fantastic tool. It's available on GitHub. If you have a public repo, you can actually run CoQL free of charge. When someone does a pull request, it can actually just check your code statically. It's a fantastic tool. It basically creates a database of your code, and you can query it. Almost like that's the QL part of CoQL. Prefast is another tool. It's a C++ tool. If you compile C++ code with /analyze, you're actually using Prefast, even though you don't realize it. If you look on the disk, you'll see a pfx.dll, and that's the actual, it's actually Prefast. Fuzzing would easily find this as well. If all of these fail for some reason at runtime, then GS, which is a compiler option, which actually today is enabled by default, would actually find the bug at runtime and kill the process dead. And we have other defenses like address space layout randomization, no execute, control flow guard, many other defenses as well. They would all swing into action. What's really cool about those things, the last two, is they are fail-fast mechanisms. We detect there's an error and kill the process dead. Now people say, well, the process is dead. Yes, the process is dead, but it sucks less than running malicious code. Yes, it sucks. It sucks that the process is dead, but you've also got a nice clean stack trace to where the failure was, which is really nice. But yeah, it sucks less. But it sucks less than running malicious code. So Slammer was a bug in C and C++. Well, actually in C. This slide is actually a very difficult slide for me to talk about because I basically was brought up on C and C++. My very first job at Microsoft was supporting the C compiler and the Windows SDK. So you can imagine I've got a long love affair with this stuff. How many of you remember the Windows message pump? You're old. Seriously, how many of you realize, oh my, okay, how long have we got? How many of you realize that a Windows GUI app works by passing messages around? Okay, you're slightly less old than this guy. All right. Well, at least you know that. That's really important. Yeah, people don't realize, when you click on a mouse, there's a message that's sent to your window handle, WM_L mouse down or button down or something. Yeah, it's all passing messages around. The fact that we abstracted that away is kind of sad, but by the same token, that stuff was an absolute pain in the backside to write. Anyway, so this is actually a very difficult slide for me because I have a long love affair with both C and C++. But there's a thing called undefined behavior, and all programming languages have some level of undefined behavior. Here's a good example in C and C++. How many of you are familiar with the post and pre-increment operators in C and C++? Same it's in C# as well, right? So if you do something like A++, plus, A, plus A, plus A++, what's the result? It's undefined behavior because the compiler can evaluate that in any order it wants. It's undefined behavior. But, no, actually, no, I was going to talk about Rust there, but I won't do it yet. So undefined behavior can lead to insecure code. And it's very easy to get undefined behavior in C and C++, most notably memory safety issues, memory corruption problems. And so the fourth bullet point here, it's hard for me to say, but it's time to move away from C and C++, even modern C++. And people say, well, you can write safe C++. Yes, you can, if you do it all the time and do it correctly all the time and everyone gets it right all the time, and you don't fall back to using the non-STL, the non-standard template library functionality, and there's no arrays to pointer degradation and that sort of stuff. It's just too easy to get it wrong all the time. And so it's time to start really reconsider the role of C and C++. Dave Weston, the corporate VP in Windows, we had him on the NDC Security podcast, and I said, why don't we're talking about Rust and all sorts of other stuff, and I said, why don't we just tell people use modern C++ and stick with modern C++? And he said, Michael, he said, that's a terrible North Star. He said, because it's too easy to get it wrong. And next thing you know, you've got undefined behavior, you've got memory corruption, you've got remote code execution. You're back to square one again. We need to focus on languages that actually allow you to write correct code from the get-go. So how many of you are familiar with this line of code? I'll just imagine all of you. All right, so this is the stir copy, right? You're copying the okay, let me explain it. You're copying the source buffer, into a destination buffer. C copies until it bumps into a trailing null. So we're always told to replace that with this. The problem with the first example, is if the source is bigger than the destination, in other words, the trailing null that says this is the end of the sentence at the end of the string, if that's bigger than the size of the destination buffer, you overflow the buffer. And now you've got memory corruption. So everyone says, well, just use stir ncopy and put n in there, and n is the size of the destination. That makes sense, right? It actually doesn't. So if you look at the way a string works, it has a trailing null at the end. That says this is the end of the string. If you don't believe me, this is what it looks like in the debugger. If you look at the last byte there, it's a zero. It's a trailing null. So that says this is the end of the string. So here's a pop quiz for you guys. How many, and just humor me, even if you don't know what it is, just take a guess. How many of you think n should be just the length of just the data, the hello world? So how many of you think it's just that, it's just n? How many of you think it is that? Oh, come on, humor me. Okay, I'm going to say half of you. Okay, how many of you think it's n plus 1? You've got to include the trailing null. The other half. Half of you is wrong. I don't know which half it is, though. But one half of you is wrong. I actually generally don't know which half, because you should never use stir ncopy. By the way, Microsoft, stir copy, stir ncopy, stircat, stir ncat, gets, sprintf, and all their evil brethren, they're all banned. You cannot write code with those. You saw the code example I gave with Slammer. Those sorts of things will come into play and prevent it from ever compiling. So the point I'm making here is that even this simple thing everyone gets wrong as well. So we need to move to only using memory-safe languages. The good news is that the industry as a whole is starting to do this. And for me, it really falls into two categories. Actually, at Microsoft, it really falls into two categories. Rust for systems programming, low-level operating system, databases, that sort of stuff is written in Rust. And then for non-systems programming, which is kind of like everything else, C#, Java, Go, TypeScript. Notice JavaScript is not on that list. There are no words to adequately describe how much I despise JavaScript. And the fact that you are laughing means you agree with me. So let me give you some examples why I think JavaScript is an absolutely atrocious language. What the hell is going on? I don't even know what the heck's going on here. I don't know. You got a string minus a number is 8. That's a syntax error in my book. A string plus 2 is actually 102. That's a syntax error in my book too. String 10 minus string 2 is 8, a number. Okay. And actually, the funny thing was, I actually thought the next example was actually correct until I realized that the minus is before a string. How can you have a minus string? And the result is 10 minus 2. I mean, they're all different. Anyway, look, I realize there's some JavaScript wonks in here probably like cringing right now, saying, Michael, why don't you just learn the language? No. I'm a big believer in correct programming. Like, no, it's just correct. People say, well, that's correct. There's a subset of correct to me, which is no surprises. Let me keep going. Then you got this. Let's sort this array of bananas, apples, cherries, 10, 2, and 3. 10, 2, 3, apple, banana, cherry. Syntax error. Or this next one, 10, 10, 10 dot map parsing gives you 10, not a number, and 2. What's the next one? Oh yeah, apparently an empty array is actually the same as a not empty array. By the way, all this is actually straight just in the console, right? I've not done anything special, I just typed it in the console, in the developer tools console in the browser. Well, I mean, come on. 1, 2, 10, 21 dot sort is 1, 10, 2, 21? Anyway. Not a number is exactly the same as not a number. False. Now, the IEEE expert, yeah, there's always one. The IEEE guy is like, oh, well, everyone knows that comparing not a number to anything is always false. So what about this one? Type defined not a number is exactly a number. True. Okay. I'm not done yet, by the way. An array plus an array is an empty string. An array plus braces is an object. Function braces plus an array is 0. Function braces plus function braces is not a number. I don't know about you, but anyway, I'll leave you one last one. This one's one of my favorites. This is how you get the word banana. B plus an A plus A plus A is banana. So there's actually, I was going to say there's some logic behind this, but I don't think you can use the word logic here. BA, okay, I get that part, plus, what it's doing is doing plus A. It's doing a unary plus on the letter A, which is not a number. So that's where the NaN comes from in the middle. It's not a number, and then a lowercase it to hide the fact that it's not a number. Anyway, that's how you get banana out of that. Anyway, so don't use JavaScript. But you should use TypeScript. I mean, I took the exact same code, threw it into TypeScript, and look, half of them are syntax errors. Just use TypeScript. It just transpiles down to JavaScript, but at least getting that front-end correctness check, if nothing else. It's a way better language. All right, back to C and C++. So I mentioned before that if you're writing, we should really be thinking about deprecating C and C++. Again, a very, very hard thing for me to swallow because I do adore both languages. By the way, there are 2 languages, it's not one language. So at Microsoft, what we're doing is, so Mark Russinovich has made it plainly available and plainly obvious to people in Azure, in our cloud environment, that there's no new C++ code to be written. It must be Rust. And we're now refactoring huge quantities of C and C++ code as well over to Rust. System code. Not an easy job, but it's something we just have to do. So some of the pros of Rust, very, very fast. When people say, oh, on par with C and C++, no, as fast as C and C++. No garbage collector. This is huge. Don't get me wrong, I'm a huge fan of C#. I actually like Go as well. But I don't like the garbage collectors, especially because you can't control, you don't have complete control over performance. In other words, what I mean by that is you don't know when the garbage collector is going to kick in, and all of a sudden you've got some delays going on. And if you've got something that's taking 1 million requests a second, you probably can't afford to take that garbage collection hit. Compile time memory safety, which I'll talk about in a moment. Lack of undefined behavior, huge detail. Again, I'll talk about in the next slide. Compiler errors are actually useful. They are really useful. You almost get like a whole screen of text explaining why the error is what it is. Massive library support, they're called crates in Rust. The last one at the bottom there is ownership and borrowing. That's one of its key safety mechanisms, this notion of ownership and borrowing of data, and I'll give an example of that in a moment as well. Some of the cons, steep learning curve. It's a huge learning curve. It takes a long time to learn Rust and to become proficient at it. It's another language to learn. You've got a whole other tool set to deploy. Evolving Windows API support. We're doing a lot of work here. to provide crates that interface into Windows. And one of its biggest cons is ownership and borrowing, because it's such a difficult concept to get in your head. Rust is a huge thing at Microsoft. I actually just snapped, like literally at the airport on the way out. The Rust newsletter came in at Microsoft, and I emailed the guy, and I said, hey, do you mind if I take the screen grab of the top of this and just paste it in the slide deck? And he said, yeah, go for it. Rust is a huge deal at Microsoft. There's a whole infrastructure, a whole bunch of people who work on this stuff. It's huge across the company. There are some Rust correctness guarantees. The first bunch of them, these are all compile time guarantees. This is at compile time, not at runtime. These are all at compile time. All these buckets of things like use after free, double free, array indexing, going off beyond the end of an array, all that sort of stuff, they're all prevented at compile time. And then at the bottom, 3 are really interesting. No abandonment problems with mutexes. How many of you have written multi-threaded code? How many of you enjoyed it? You two are so lying. It's like, there's no way you enjoyed writing multi-threading. Okay, you two that said you enjoyed it, how many of you, of the 2 of you, how many of you, it worked first time? Precisely. Was it in Rust? Oh, okay. Okay, yeah, okay, you didn't lie. Okay. Okay, no. Okay. Did it compile first time? No, it didn't. It compiled first time, seriously. Okay, so this is actually really important. Like things like forgetting lock mutexes. One of the big problems, you can have these things called abandonment semantics, where you can have a thread take a lock on something, and then another thread wait for it, and then this thread dies or something, but the lock isn't released. So now you've got another thread that's now locked, because this thread's gone away. How many of you know that Windows actually has 2 types of mutexes? One of them is hidden from you, you don't realize it, because it's not really raised. So back in the day, Windows had a lot of OS2 backward compatibility in the very early days of Windows NT. And so the mutex that came from OS2 did not have abandonment semantics, which means that if a thread dies holding a mutex, the mutex stays locked. And Dave Cutler said that's brain dead and called it a mutant instead. And then created a mutex that actually is the same as a mutant, but with abandonment semantics. And that's the mutex that you all know and hate in Windows, but that's the actual real mutex. But the original mutex was actually called a mutant because it had no abandonment semantics. But you got things like critical sections, spin locks, semaphores. The nice thing is that Rust will guarantee at compile time that you will not get these locked mutexes. Same with data races across threads. And this, a lot of it boils down to lifetime guarantees, which is actually something else that Rust really makes explicit. You could have 2 arguments going into a function that have 2 different lifetimes. Like one may exist inside a loop, and then in an inner loop, maybe the other variable. Well, if the inner loop finishes for some reason, that second variable is no longer valid. And Rust will actually detect that at compile time. The downside of that is that compile times are slow, right? Because it's doing all this work ahead of time. But the nice thing is, if it compiles, it is thread safe. That's huge if you've ever written multi-threaded code. If it compiles, it's thread safe. The problem is getting it to compile. But once you get it to compile, at least you know your code is thread safe. All right, so one thing that I will, if you want to learn Rust, here's something I'll tell you up front you need to know. The borrow checker will drive you absolutely nuts. How many of you have written some Rust or played or dabbled around with Rust? How many of you are hitting your head against beyond Hello World, how many of you were hitting your head against the borrow checker? Yeah, all of you. So look, I realize this code, people are looking at this code who are Rust wonks like, oh, Michael, you would never write Rust code this way. That's true, you wouldn't, but just humor me. So here we've got in line 2, let name equals a string called Michael. And then I pass that name to a function called say hello. Now I go in there, and once say hello says, hello Michael, then I say print line again, line 6, say welcome back Michael. So what would you Rust wonks, keep quiet. Everyone else, what would you expect to see on the screen? would you expect, hello, Michael, then welcome back, Michael? Would you expect that? Yeah. News for you guys. See that red squiggly under the word name on line 6? This doesn't even compile in Rust. And the reason is that variable name, you've passed ownership of that variable to say hello. Essentially, the variable name no longer exists. Now, there's ways you can, look, you pass it by reference. You wouldn't even write this anyway. You would use a string literal, which will be fine. But the point is that borrow checker is you're going to be mad at the borrow checker for a long time until it finally clicks. As I mentioned before, the good news is that the error messages and warnings you get from the compiler are fantastic, will really help you. There's a great talk that was done at NDC TechTown, well worth looking at. It says Rust is not about memory safety. Yes, it is. But it's not just about memory safety. I think that's a more accurate title. Let's go back to some of today's security pressures. The big ones for me are a huge need to shift left. Also moving to DevSecOps is a huge deal. And also this massive cognitive burden. I can't stress this enough. A term that we're using at Microsoft right now is the word toil. There's a lot of toil to know what to do. People are not necessarily security alpha geeks. They're just not, which is actually a good thing. Because if everyone in the world was a security alpha geek, we would never ship a software product ever again, right? Because it would be really secure, but just never ships. But you want to give people enough knowledge that they do the right things. There's huge cognitive burden on our engineers today, huge amounts. And so we're doing as much as we can to relieve as much of that cognitive burden as possible. Then we have bad actors. That's why we wrote that book, Threat-Driven Software Development, is an understanding of what the bad actors actually do and how they ply their trade. And then finally, you got things like certification and regulations. I realize these are not security. They're not, but they have a big impact. So this is where the Microsoft Secure Future Initiative came in. Think of SDL as being very, very code-centric, but SFI being much, much broader, with a big focus on ops as well. A lot of issues that we have over the years have not just been code, it's been configuration, it's been ops. A lot of the sort of precursor to SFI was a series of attacks by a threat actor named Storm 558, and they were attacking a lot of, especially US organizations, going after tokens, authentication tokens, or authorization tokens. And so we came up with this SFI, which is a big superset of SDL. It encompasses some of the SDL stuff, but a big focus is on ops, not just on code. So the SFI has 3 pillars: secure by design, secure by default. To me, they're some of the 2 most important. Secure by design, getting everything right. Secure by default is recognizing you never will. That's a really healthy tension to have. It's like, hey, let's just get all the code right. Well, what happens if we don't? What happens if we can't? What happens if threats evolve that we don't even know about? So that's why we have the secure by default. It's having secure default configuration so that the chance of attack is reduced substantially, or perhaps the blast radius, because of network isolation, is reduced substantially. The main parts of SFI are protecting identities and secrets. This is probably one of the biggest areas because of the way authorization works and the way the attackers are going after identities. Same with secrets. If I can get your credentials and I've got your credentials, protecting tenants and isolating production systems from attackers, protecting networks, also including things like network isolation, huge deal. There's a big focus in SFI on isolation, isolating networks, identities to reduce that blast radius, assuming that attacks will happen. Monitoring, detecting threats. This is really the ops part of it. Is we recognize it. So in the red team, we found issues where there's not been good detections. The job of a red team is to apply pressure to the environment. We have incredibly skilled operators in the red team, and the whole point is to apply that pressure to our environment so we can see how the blue team reacts, and so we can find out where issues are in the environment. When I say apply pressure, that's just a euphemism for attack, but it's essentially what we do. And then finally, making sure we have better response, because vulnerabilities will happen. What's the response? How do we remediate those issues? And then down the bottom is this continuous improvement, especially paved paths. And I'll talk about paved paths towards the end. SDL supports so many of these SFI principles. SDL sort of dovetails quite nicely into what a lot of SFI does. But again, SDL is very code-centric. SFI has code issues, code concerns, but it's much, much, much broader, especially around ops. The other big change that we've had over the SDL over the last few years is to move to this continuous SDL model. In the old days, you have all this activity tracking, right? Where are your threat models? What are the results? Are you doing? You're running these CoQL queries. What warnings are you getting? Are you resolving these issues? What time frame are you using to resolve these issues? Huge checklist that people would have to go through. Massive amounts of cognitive burden. Lots of process. So what we've moved to is something that's a lot more streamlined. And rather than just eliciting, pulling the data out of things, we get these tools to push data to a central location so that things can be tracked. So we can actually see, is everything green? Sort of get green, stay green. Is everything green? Oh, there's something turned red. What's going on here? Oh, they haven't run CoQL or whatever, right? We found some banned APIs. Compiling failed because we found some banned APIs, that sort of thing. And then we can drill into things. So it's much more sort of event-focused, and it's more, considerably less friction. I'm a big fan of reducing friction. If you can reduce friction, then you can get engineers to do what needs to be done, because it's easiest to get done. Another big one for us has been detecting secrets and preventing secrets. By the way, detecting secrets means detecting secrets in the pull requests as well, so that we can detect them before they're pushed into the source code. So we'll do things like pull request blocking. What's interesting also is that we have this thing called the Common Annotated Security Key, or CASK, which is a way of annotating a secret so we can see that it's actually really a secret. If you see like some random, in some code, like just some random string, what is it? You have no clue. Is it a key, an encryption key? Is it a passphrase? Is it a secure access token to access some resource? What the heck is it? What we now do is we prepend an annotator that says this is a blah, blah, blah. So for example, this example right here, and by the way, this is a real key, which I have now deleted, so don't try using it. It says GitHub_pat. So it's a personal access token in GitHub. And so we know it's a GitHub pat. So if we see that random string and it's got GitHub pat at the beginning, have a guess what it is? It's a GitHub pat, which means that we can detect and tell you you've got a GitHub pat in the code. And we know precisely what it is with 0 false positives. So that's really huge. So you should be going to take a look at CASK and start annotating your secrets with CASK identifiers. Makes life so much easier for finding real secrets. So the big question I get a lot, with SDL, now coming up onto 25-ish years, have we actually made any progress? And the answer is emphatically yes. Absolutely we have. Whole categories of vulnerabilities have just gone. You don't see trivial memory corruption anymore. You just don't. It's been replaced with complex memory corruption, which you could argue now the hard work starts, right? Because we found the easy ones, now we've got the difficult ones. And that's why we know those difficult ones exist, primarily because of C and C++. And so we can't fix all those things, and we can't find all those things, and we know that every C and C++ product out there has probably got some latent memory corruption vulnerabilities that are very, very difficult to spot. Through static analysis, through dynamic analysis. And so we have to move. And Microsoft, that big move is towards moving more code to managed languages or memory-safe languages like Rust and C# and Go, not JavaScript. However, with all that said, identity does add new wrinkles. If I look, one of the big things that I do is I look at the vulnerabilities that are found from the red team operations and say, okay, what can we learn from these things? You've got to realize these people, I made a bit of a flippant joke at the beginning about evil people. They're not evil. They're just really, really good, like world-class talent. And you sometimes think to yourself, how the heck did they find this thing? But a big part of what I do is understanding what those issues were, and you'd be amazed how many are related to identity. Because that's the new boundary, right? The network was historically the boundary. It still is a boundary, don't get me wrong. It's a very important boundary. But the boundary now is really identity. And if I can compromise that, then I'm now in the boundary. And that's why authentication, sort of identity in general, authentication and authorization vulnerabilities are of real concern. I'm not going to go into the stuff on the right-hand side of the diagram. It's a whole nother discussion unto itself. But if you see like admin consent, unused or dangling redirect URIs, delegated permissions, that combination is really terrifying. So, and also device code flow. Any of you have a solution that uses device code flow? You know what? Even if you did, you would never admit it. We've deprecated device code flow because it's just so dangerous. In fact, I think, and I realize it's been recorded, so I hope I'm right here. That's what I understand today is Entra ID by default has device code flow disabled by default because it's too easy to phish. So I want to give you a real example. This is a real Microsoft Red Team operation. The operators snuck into a building. There's a building, the door didn't close. By the way, I want to point something out. The Red Team, we have an objective. That's it. And we do whatever it takes to get to that objective. Whatever it takes to get to that objective. And in this example, a door didn't close properly on a building. By the way, this is not James Bond. This is a real operation, a real Red Team operation. So a couple of people snuck in and put, in one of the kitchenettes, put some little, give us your feedback on, what's the state of the kitchenette? Scan here with the QR code. That was a phishing hook. And we found an app that we could take advantage of that had a dangling URI. So if you know the way OAuth 2 works, there's a redirection URI. Well, one of the URIs was dangling. In other words, it was a DNS name, but there was no code behind it. It was dangling. So we wrote the code that was behind the URI, and now we've got the person's token. Well, actually, it was a refresh token, but that's all we need. We're now got a refresh token. We can now get a bearer token. Now we can do whatever that person's doing. Even if they've gone through the multi-factor authentication phase, we've now got a valid token that we can use. So that's a real example. Then once we've got those tokens, we could do all sorts of fun. That's all I'm going to say about the op. There's a lot more to it, but that's all. That's the bit you need to know. All right, what about the role of AI in all of this? This is a Microsoft presentation. Of course, AI is going to raise its head. We have found that basically developers plus good AI leads to incredible productivity, amazing productivity, especially around security. There are some challenges, of course. Vibe coding. We've all seen the big, people having their job descriptions. I debug vibe-coded code. Because a lot of the code isn't fantastic. But if you have a very well-grounded model and you have very good examples, you can actually do a lot of increased velocity when it comes to software development. I want to move to the last one, which is you've got to make sure you've got reliable sources for your models, your LLMs, if you're going to use them for production code. So the SDL is really adapting to AI as well from a security standpoint. You've got to think about using AI securely, but also securing AI. They're two very different things. A bit like security features does not equal secure features. It's a similar idea. We've now got threat modeling for AI. We're now doing things like AI system observability requirements in the SDL if you're building a system that uses AI. AI memory protections, and I don't mean RAM, I mean just the memory, the context that goes into a large language model. The middle one there about agent identity and RBAC enforcement, if you think about it, this is a classic security thing, right? Like running at least privilege, we all know about least privilege, right? And then strong RBAC policies, strong authorization policies. That's just classic stuff. That's got nothing to do with AI, but it's very important when you're considering protecting AI. modeling, protecting models, like where do they go? Do you pull like some random model from some random place on the internet? That's just as bad as downloading random code versus pulling them down from a well-vetted, correct repository. And then shutdown mechanisms. When we detect that an LLM is being used for evil, like how do we shut things down quickly? So threat modeling versus threat modeling AI, we now push inside Microsoft, threat modeling for AI systems. If you look at traditional threat models, there's a big focus on the data and the software. But the big part of AI threat modeling is understanding those AI models and understanding the fact that they're not necessarily deterministic. Right? You may get multiple responses, different responses from the same input. So we look at things like data poisoning, like how are the models actually protected? How do you make sure a system does the right thing? So I worked on some, when I was in Azure Data, I worked on a Copilot for Cosmos DB. And a big part of that was we assumed that if you say, how do I query this database for blah, 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 we assumed that the query that came back was wrong. That was our assumption. And so we made sure that you connected as a low privilege user back to Cosmos DB when you were doing this. Because we assumed that the SQL statement that came back was going to be malicious. Because it's non-deterministic, where we don't know what's going to come back. There's other checks that we make, there's a lot of checks that we make as well to make sure that the query actually represents what you originally asked, but we also assume it's going to be rogue. So you need to think about those things when you're building systems. And then you got really simple stuff, just the most simple stuff. Like I've got some code up on here for analyzing or pulling apart an OAuth 2 token. Real simple query on the right-hand side there, perform a security check around this OAuth 2 code. Every single one of these things on the right-hand side, I actually did a hand review of every one of them. They're all correct. In other words, they're all real bugs, every single one. And that query is dumber than a bucket of rocks. I mean, amounts of effort required on my part to write that is zero. And the benefit that I get from it is incredible. Now, that's even without data flow analysis. So imagine if you can start marrying static analysis with AI. So then you got more complex queries. We actually had a spate of issues inside Microsoft where there were some OAuth 2 token issues. And so we thought we'd go in and actually really look at massive amounts of source code and see if we could get to the bottom of some of these issues. This is an example of actually one of the prompts. Actually, it's abridged, so it would fit on the screen. But this is just an example of one of the prompts that we used. This next slide will absolutely blow you away. If it doesn't, I'll be shocked. I mentioned before about this cognitive burden and this huge toil on engineering staff. So one thing I mentioned before we were working on, and still are working on, is updating a lot of sort of OAuth 2 authorization vulnerabilities caused by not parsing an OAuth 2 token correctly. And so if you look at, this is to do with the Entra SDK migration, so we're moving from some old code, moving the whole of Azure to use the new updated, more secure Entra SDK. If you look at the mean time to resolve, now don't get hung up on the time frames there of 5.9 months. Man, that's a long time, but this is code that is so deep in the bowels of Azure, we have to be very careful how we deploy it. So look at a human only is 5.9 months, but with some of the new AI work that we have using agents, 1.6 months. Or another one was time to understand the technical guidance plus the actual changes all the way to a pushed pull request. 13 hours down to 15 minutes. We then measure the result to actually double check that the result is actually correct. And we're up in the 99, 98, 100% correct. Better than a human being. That's pretty mind-blowing if you think about it. So it reduces a lot of human toil. But what I want to point out, notice we didn't say AI in the right column. It's human plus AI. There's always a human in the loop. I've got some links in the speaker notes for this particular slide. You should go and look at all of these. So those figures that I showed you were before. The woman involved, Jenny Ferris, She wrote a lot of this material, and it's well worth looking at. It's how we're using agents to actually increase developer productivity with very high confidence. However, I will warn you about one thing, and that is that LLMs don't get the code right all the time. They just don't. You've got to make sure you have very good models that understand the correct, have good code as its base data. So here's an example of a quick query I wrote. Write some C# code that takes 2 strings and creates a SHA-256 hash of the 2 strings. Here's the result from Gemini 3, and it's wrong. I then did the same thing in ChatGPT 5.2, and it's wrong. Did the same thing in Claude Opus 4.6, and it's wrong. And then I tried Grok 4, and it's wrong. They're all wrong. And the reason is they're taking 2 strings, concatenating them, and taking the SHA-256 hash. Anybody know the vulnerability class? It's a length extension attack in hash functions. So basically, you never, ever take 2 strings and slap them together and hash them. You never do that. You can do it with SHA-3, but no one's using SHA-3. But the other ones you can do, but you use SHA-256, SHA-512. This is a vulnerability. If you want to know what the vulnerability is, without going into all the details, let's say I've got a secret message, not secret, but it's an authenticated message. So a secret plus the actual message, and then hash it. The secret, or the message could be attack at dawn. But I could actually take that hash, the result of that, and actually create a new message, which is attack at dawn, except if it's raining, then attack at 1. And it will still result in the correct hash without me knowing the secret that was added to the hash. That's called a length extension attack. Very subtle, but very real. All right, let me wrap this thing up. So some core by the way, originally this was like 3 lines. And then I just kept going. So these are the core sort of takeaways from all of this. Absolutely, if you're using C and C++ today, have a strategy for moving on to memory-safe languages. Use languages that support correctness, not JavaScript. Stop the bleeding. What that means is stop writing or put processes and tooling in place to make it harder to write new insecure code. It's not going to be perfect, right? But at least stop the bleeding. Burn down technical security debt. You could argue that a lot of what SFI is doing is burning down technical security debt. Go and look at some of the SFI reports where we actually talk about what technical debt we've removed. Evolve, because threats evolve, right? As new threats evolve, so there's a big part of what we're doing at Microsoft now revolves around getting OAuth 2 tokens right. Paved paths are absolutely critical. What that means is make it as frictionless as possible for developers moving forward. Standardized libraries, like thou shalt use this library. Don't go rolling your own code, use this library. Create correct and actionable guidance. Don't just say, hey, don't do this. As security professionals, we're very good at saying, don't do this, because that's dumb. But we're not very good at saying, do this instead. And here's how to measure whether you're doing it correctly. Be careful with regressions caused by security. We see this. It happens. I wouldn't say it happens a lot, but it happens when you don't want it. So be very careful with regressions that you introduce with security. You've got to automate as much as possible. Cognitive burden and toil are a huge concern on engineers today. How many of you have heard from either yourself or have heard from your staff or colleagues or whatever, just this whole AppSec thing is just a burden. There's just so much we need to do. None of you? What the hell are you doing? Oh, thank you. Treat initial AI code as a junior developer. Until you get good models that produce good quality code, just treat it as a junior developer. There must be a human in the loop when it comes to AI. I've said this for I don't know how long. Security features does not equal secure features, never has and never will. OAuth code is today's the weak point. Like identity code is a huge, huge weak point. And then input validations are still a massive issue. If you look at prompt injection, indirect prompt injection, model poisoning, and so on, a lot of those are just input validation problems. That's all they are. And to give you an idea of how much of an issue this is, I actually took from the book, one of the book drafts, the identity chapter was supposed to be 25 pages long. I stopped at 60. Look at that's just the section on validating OAuth 2 tokens. That's terrifying, in my opinion. For something so critical, you have to write 40 pages of stuff. So I'll leave you with one last thing. This is from a slide deck that I wrote in 2002. You can tell it's from 2002 because it's 4 to 3 aspect ratio. There are only 2 types of security issues: input validation problems and everything else. Although I gave a quick talk of some of my colleagues, and they said, "Hey, add this one," and off by 1 errors. Whatever. All right, I'm done. I hope this is useful. I realize it's an absolute, ton of content. By the way, that's 50 slides. If you don't know, I hope you found that of use. If you have any feedback, comments, I'm going to be milling around. I'm more than happy to take your questions. There's the feedback form up there. I hope I was asked to add it to the slide deck, so I hope it's not a rickroll. Anyway, thank you so much for your time. Appreciate it. Oh, thank you so much. I appreciate it. Thank you so much. I appreciate it.